Shoot. Yep. All right. Welcome back, everybody. Today, our topic is going to be conditional statements and loops. Might seem like a lot. We're going to do if statements, while loops, and for loops, but if statements are the main work here. While loops are a special if statement that has a jump at the end, and for loops are a special case of while. So those are going to be super easy to implement. Last week, we added conditional statements, so that gives us these conditional operators. And right now, they're represented by LLVM's I1 data type, which we're using for our Boolean values. Hey, Tim. Could you just close the door? Jeez, thank you. And so the topic today is one of my favorites. We're going to go over conditionals and loops. So again, if statements, while loops, for loops. Up until now, we've implemented some very fundamental features that most imperative languages should have. Variables and assignments and operators and whatnot. But we haven't implemented any complex control structures. So that's what we're going to be doing today. If statements, those are control structures. So this is our first. I'm excited. And let's get right into it. So this is a quick update on our BNF grammar. We've kind of glossed over it the past couple lectures, but so you're going to see that we have braces around all of our statements now. I'll get into why we do that. We've got our print expression, we've got our declaration expression, we have our assignment expression, we have now if statements, and we have while statements. I wrote this BNF before I decided to also do for loops. But for loops, I think we all know what those look like. So yeah, we wrap all of our statements with braces now. The reason we do that is because of something called the dangling else problem. So this is a problem in parsing, and different implementations of how to solve it will lead to different program behavior, which is kind of a big deal. So it occurs when you have nested if statements and you have an else statement. And if you don't use brackets, you end up with, or some kind of parent concept. You end up with an ambiguous attachment of the else to one of the ifs. So this code sample right here, let's assume it's not Python, it's some language that's not indentation based. We have these two if statements, and then we have an else statement. And can anyone tell me which if the else belongs to?
Yes.
No, you can't. Nope, not that one. We don't know, because we don't know anything about the language. So in C, yes, in most implementations of compilers, it'll be the first, or it'll be like a greedy kind of parenthood. But again, that's implementation specific, and we could easily make it so that the else attaches to one or the other. But I don't want to do that. I want to make it very explicit what our programs are doing. So we are not going to allow the shorthand if, for, while syntax that we can do in C, where if it's just one line, then you don't have to put brackets. Right now, we are always going to require brackets. So this is the plan for adding if statements. We need to add in tokens for the word if, the word else. We need to add parenthesis tokens, and we need to add brace tokens. That's the curly one. We need to add a custom if statement parser, and we are also going to update our generic statement parser. I'll go into that in a second. We are going to implement generators for LLVM labels and jumps, and we are also going to add a testing suite to our language. So at this point, we've got operators, we've got assignments, we've got declarations, we've got if statements, we've got loops, we're about to add functions, we're about to add structs. We've got so many different features, and we want to make sure that when we change one of them or we modify our entire parser or something, that we don't break any other behavior. So we're going to go over a very simple PyTest implementation. So I'm just going to talk about the statement parser updates for a second, and then we'll look at them. we had to make some significant changes to the statement parser to support conditional statements. Could someone let that person in? And if you could just leave the door cracked. Cool, thank you. So, yeah, we have to make some changes to our statement parser. And the reason why is that when we have our AST, the way we're going to do it is we're going to add a middle child to our AST node. And the left child is going to be the AST that is going to generate the value of our condition. The middle child is going to be the contents of the if block, and then the right child is optionally going to be the contents of the else block. And the issue is that the way I've just described to do it, we need to have an entire subprogram stored in an AST node. So the issue is we have to undo our generator optimization where we parsed statements one at a time. Now we are going to parse entire blocks of code into an AST. We can redo our optimization later on when we get to functions, but at this level of granularity and with the way we've structured our compiler so far, I think it makes sense to do it this way. So, covered those two. Yep, all right. And the third thing is that we are going to start gluing ASTs together. So, because we've got specific blocks of code that are context sensitive, like, the code that's inside an else and the code that's inside an if are context sensitive because, even if they could do the same thing or even if they do different things, they'll be executed conditionally. So we need to glue our nodes together in a way that we can process them conditionally and all that. So I'm going to add in an AST glue token. All right, let's look at the parser now. And let me open this on my screen. All right. So, where's my mouse? Right there. So let's look at AST node real quick. Right here. So yeah, I've added in a middle child. We had to update all of our calls to the AST constructor because of that, but nothing really complicated. One thing to note, I did add this property. So if you see an AST node.type, it's just calling token.type. I got tired of typing it out a bunch, but okay, statement parsing. So first I want to talk about the changes to the general statement parser. This is a really bad diff. It's hard to read. I'm just going to open the file. View file. All right, so the way things work now is we've got a root AST node and we have a left AST node. And the idea behind these is that the root is going to be the output of all of our individual statements. And then you see we scan this left brace here. And then when we get to a right brace, we return this left node. And what left node is as this while loop executes, if we don't end up returning anything, we are going to glue together root and left. And this allows us to put together a big old AST that has a bunch of individual statements in it. And we'll see in the code generator later that we've modified it so that whenever we encounter an AST glue node, we will generate the code for the left child, the middle child, and then the right child. So it doesn't have any special logic, it just generates code for its children. So that's how we're going to stick together blocks of code that are within if statements or something. And yeah, so what do I want to cover next? Okay, yeah. And so now we're going to cover our if statement parser. So this should be pretty simple. We match an if token that we've added. We match our left parenthesis. We parse a binary expression. And right now, I'm just adding in this arbitrary limitation that we need to have a comparison operator as the root token type. So we could just say, like if one or something. It would not be too complicated to add that in. But I want to deal with that when we get to giving assignment statements values. So I want to cover those sub-expression things at the same time. So right now, yeah, we're just going to say that branch statements currently require a conditional operand. We match a right parenthesis, and then we call this parse statements, which is our general statement parser. And it's going to handle all of our brace matching for us, right? And whenever we terminate this function, it's just going to give us a AST that has a bunch of glued statements together. And then we are optionally going to have the conditional converse block, which is the statements that are within the else. And if we see an else, we're going to match one, and then we're going to assign parse statements to it. And then we just stick together. We make an if AST node. This is our condition computation. This is our inside the if code, and this is our inside the else code. So before we get on to code generation, I think it's important to talk about what an if statement looks like. So LLVM's branching paradigm is fairly similar to anything else you've seen in assembly, assuming you have seen something in assembly. There is only one branch instruction, BR, and it handles both unconditional and conditional jumps. So in this first example here, we have branch label, and then we give it label L1. And labels are just going to be defined at the bottom here, where you give it a name and then you give it a semicolon. And this is how we are going to be doing our labels. So similarly to our registers, we just want something enumerable so that we don't have to keep track of a list of strings or something. So we can say branch label L1, and that's an unconditional jump to L1. And then we have branch I1 condition, so you're giving it an I1 register, and if it's a 0, or if it's a 1, it's going to jump to the true label, and if it's a 0, it's going to jump to the false label. So nothing too complicated there.
Wait, what's a fall through?
So that's what I'm about to say. Fall throughs are where you have a bunch of code and then you just have a label right after it. So LLVM doesn't like that because it thinks that your compiler is accidentally entering compound statements. So like the contents of our if block that's called a compound statement, or else or for, or whatever. Anything where there's braces, and that's a compound statement. So if it thinks that you've generated code that accidentally enters a compound statement, it's going to get mad at you. So you have to manually branch into the label, which seems a little dumb, but it's a good thing that the backend does for us to make sure we don't have any bugs. So you're going to see that when we generate code for if and while and for, we are going to jump immediately into the next label. And then so this is what our if-else statement is going to look like. This pseudocode that I've put up here and LLVM that I've put down here, these are isomorphic, so they behave identically. We have if condition, do something 1, else do something 2. And in LLVM, what that's going to look like is we're going to compute our condition, we're going to put it into this condition register, and then if it's true, we're going to branch to the true label, and if it's false, we're going to branch to the false label. And then we also have this thing called the end label. So when we execute this do something 1, we don't want to then fall through to the false label, so we are going to unconditionally branch to the end, which happens after the false code. And then again, because LLVM doesn't allow fall throughs, we are going to unconditionally branch to the end after the false code. So let's look at AST to LLVM. Let's generation translate. Yep. Okay. Where did there we go. So, we've made a few structural changes to AST to LVM. One thing is that, we've got this AST.type property that I added. Secondly, I added this thing called parent operation, just a token type. And what that is whenever we call AST to LVM, we are going to also pass in, recursively when we call it, we're also going to pass in the operation of our current, or the token type of our current node. And the reason why is, consider that we now have two reasons to use a conditional operator. In one case, we just want to get a value and then assign it to a variable. But in the other case, we want to use it as a condition for our branch statements. And we need to handle that code generation differently. So I've added in this parent operation. And then down in the comparison operator case, if we see an if statement, then for our parent node, then we're going to compare and jump. Otherwise, we are just going to perform a comparison. So nothing crazy there. Let's look at the if statement. Oh, and I will cover this. So this is up at the top. These are special kinds of token types that have different logic than all of the expression generating stuff down here. So we just want to stop the compiler in its tracks and say, actually, you need to do this if you see this operation. So here we'll check for an if statement. And then this is what I was talking about earlier, where if you see a glue, just generate the code for all of its children in order from left to right and return none, because glue doesn't do anything. So let's look at the if AST generator, or AFT, generator. So we are going to grab an n label. Oh, hang on, let me look at something. Okay, so the thing about falling through, I guess I didn't implement that. Root dot left, middle. Okay, so I guess we are going to fall through to the true statement. I wrote this yesterday. Why was I? Okay, whatever. Let's assume that everything is fine and dandy, and because the code does work, I've tested it. But anyways, so we have this n label. We discussed what that is. We've got a false label. And we've added this up here. We've added an LVM label index that we just start out at 0, and then nothing crazy, just increment it by 1 whenever you need another label. So in the case where we don't have an else, our n label and our false label are going to be the same thing, because we don't need 2 labels there. We only need 1. So that's just checking right here. If we actually do have an else statement, then we are going to get another label. Otherwise, we're just going to stick with the one we got. And so if we've got a left and a middle, which again are our conditional computation and our true compound statement, we're going to generate those. The reason we pass in false label here, generate code, computation, generate. Okay, so this also be the false label if there's no clause. I think I might have done n label and false label backwards. I'll check if that's a bug in a second, but I think it works. So the reason we're passing in our false label, which again is so that's an LVM value. We've updated that class so that this is why I had the LVM values in the first place, is because ASTs can represent a wide variety of things. So we've got this false label. We're going to pass it into AST to LVM, and this is going to kind of just strong arm our compiler into generating an unconditional jump to false label. And if you follow the traversal of the tree, then you'll see why that does that. And then we're gonna we're gonna generate our code for the true compound statement. This is just linter checking, don't worry about it. And then so we've generated our comparison, we've generated our conditional jump, and we've generated our true code, right? And so if we have an else, then after the true, we are going to generate a jump statement for the end label. If we don't, we are going to automatically jump to the false label, which is the same as the end label in the case where there's no else, right? We are then going to generate our false label, and then if there is a else, we are going to generate the else code, we are going to auto jump to the end label, and then we are going to generate the end label. And so let me show you what those code generation statements look like in LVM.py. So so this is label generation. It's just going to be this purple label prefix, which I defined as L, and then the int value of our label. So, and then a semicolon or colon. Nothing crazy there, and again, nothing crazy on the jump statement. We branch, we say it's a label, and then we give it the label name right there. And so we'll talk about the conditional jump, I think, right? Yeah, so back in AST to LVM, what did I call it? We have right here the compare and jump function. So if we've got some kind of comparison operator, and our parent operation was an if statement, then we need to generate that statement that compares, loads it into an I1, and then jumps conditionally. So that's what this is right here. We're going to reuse our comparison function. We are not going to cast it to an I32 like what we were doing before. We are going to, oh, okay. It is generating the true label. I probably should have done this explicitly in the if generator, but there we go. That's the no fall throughs rule. We generate a true label, or we get the next available true label. We generate our conditional jump statement, which is one of these where we have branch, we give it the I1. I did this number type here. It's always supposed to be an I1, I'm fairly certain, but just for consistency. We give it the register that we passed into it, we give it its value, and then we give it the true label name and the false label name. And that's not what I meant. Control, scroll, no. And then after that, we just generate our true label. So it's going to have condition generating code. It's going to generate our true label, our generation code, conditional branch, then our true label. True code, false label, false code, and label. Just like in the diagram we saw earlier. And that is it for if statements. We didn't really have to do anything else. It was a fair amount of refactoring, but it's good refactoring and it makes our compiler more general. So the next thing that's on the docket is the PyTest testing suite. So let me go to that. Not 7, 8. So I've added in this test folder right here. PyTest expects that all of your tests are in the test folder, I'm pretty sure. This is a little helper function I wrote. It just uses subprocess to handle the running of the compiler as if you ran it from bash. And it'll it'll run Clang, and then it'll run your binary for you. So if you're doing this on some non-Linux machine where you've got a Clang binary, you'll probably need to edit this. Or if you use some different script to run your code, then you'll have to edit this. But I added in this little cleaner line. I don't know why, but on my desktop I get this setup tools deprecation warning, so I just filtered that out. And then we're just going to say assert that this thing is supposed to equal this thing, where this is a string that we give the function. That's the expected output of your binary, and then this is the actual output of the binary. And then we're just going to remove our testing files. Although, so if the assertion fails, which is a case where you'd want to go look at the code that got generated and see what went wrong, these two statements won't execute, so that's helpful. And then in our test examples, so these just use all of the tests from the examples folder. So for example, this test one, this is the, I'll show you right now, since we finished the if statement stuff. Check out conditionals. Okay, so examples test one. So this is our if statement checker, and so we've got in I and j. I is 6, j is 12. If I is less than j, we're going to print I, otherwise we're going to print j. I is less than j, so we should see a 6 output, which you can see is reflected here in the test implementation, where I say this is the output that I'm expecting. And so we can do scripts run examples test one. No issues. We will clang test1.ll, name the binary test1. We'll call the binary. Boom. We've got 6. So we know that that works. And then these are test 2, 3, and 4. Those are older tests from the previous features that we've added. At this point, it's probably a good idea to rename them, so I probably will, just so that it's not ambiguous what tests went wrong at a given time. But the nice thing is that now I can just run pytest, and it says, hey, I found 4 tests, which is these 4 functions. It's going to be anything that has a prefix or a suffix of test, and it's going to run all of my functions for me. Boom, I passed all my tests. But let's say, examples, test, let's just modify our if code. So let's make this 100. And now it's called pytest. It should fail on test 1. Boom, it failed on test 1. And once it finishes the other test, it's going to give me a summary of what happened. So it's just going to say assertion error, but it's saying if there were more assert statements, this would be a more helpful error message. But we know that we didn't get 6 here like we should have. We got 12 probably. So let me fix that. All right, so that's our testing suite that we added. And so what's the plan for while loops? Well, we need to add in a while token, we need to add in a while loop parser, and then we need to generate LLVM.loops. The nice thing is that we've done basically all of this already. I shouldn't have gone out of presentation mode. So our while loop parser is going to be almost identical to our if statement parser, except that there's no else clause yet. And similarly, our code generator is going to be almost identical, although the structure is going to be a little different. We're going to have a condition label that's above our condition computation. We're going to have an unconditional branch into it to prevent fall-throughs. Then we're going to have our conditional branch. We're going to have our inner block that gets executed if the condition's true. Otherwise, we're going to branch to the end, which is the end of the loop right there. So let's look at the while loop let's look at those real quick. Parsing statement. So, and I need to be on branch 9. And so this is our while parser. So match the while token, match the left parenthesis. We are going to parse a binary expression, make sure it's a comparison operator, match our right parentheses, get our conditional block, and then construct an AST. Very simple. And let's see the generator for it. That is going to be this while AST to LVM. So again, we get our condition label and our end label. The true label is going to be generated by AST to LVM. So we're going to unconditionally jump to our condition label. We're going to generate our condition label. Generate our condition computation code and give it the end label as what to jump to in the false case. We are going to generate our inner block of stuff that happens when the condition is true. We're going to unconditionally jump to our condition label, and then we are going to generate our end label. And I will pull up this again. Git checkout 09. And so I'll cat examples test 5. So this is a while loop that should print out the numbers 1 through 10. So let's do scripts run examples test 5. Let's look at the LVM for it real quick. So allocating space. This is our condition label right here. And all of this is computing it. You can see that we load some values and then we perform a comparison on them. Conditionally branch to the true statement or to the false statement, which is the end. And then this is going to be all of our code that was inside that while loop. So let's see if it does what it's supposed to.
So LLVM has like a set less than equal to operation?
This is, where was that? I compare.
Yeah.
So this is integer compare, and this is signed less than or equal to.
Oh, okay, sounds good.
Yeah. But yeah, it's going to store either a 0 or a 1 into register 10, and that's the I1 value type. So that's what we use for booleans. So Kling didn't put up any fuss. Default name 1 through 10. Very cool, right? What's even cooler is that for loops are even easier to implement. All we need to do is add in a for token and add in a for loop parser. And the reason for that is because for loops are a special case of while loop. The only difference is that this statement right here, that just gets executed before the for loop. This is our regular old condition, and then this happens after our inner statement at every loop. So these two loops are identical, and we're going to use that feature to build them really easily. So let me show you branch 10. So this is our for parser. We're going to match a for, we're going to match a left parenthesis. We are going to get a assignment statement as our for preamble. So I believe in C and a few other C-like languages, you can actually put like whatever you want into those three blocks, but we're going to just for right now assume that it's always going to be an assignment statement, a comparison operation, and then another assignment statement. So get the assignment statement, match a semicolon, get our condition tree, make sure it's a comparison operation, match another semicolon, and then get another assignment statement, match a right parenthesis. So, and then we're going to have our conditional block, which happens inside the loop, right? And so we're going to do a couple glues here. So we are going to glue together the conditional block and the for postamble. And remember, that's basically saying generate the code for the conditional block, then right after it, just generate the code for the postamble, which is that, I equals I plus 1, right? After that, we are going to glue that as the right child onto our condition tree, and that is going to be a standard while loop like we had seen before. And then after that, we are going to glue the while loop on the right to the for preamble on the left, which basically says do the preamble one time, generate the code for it, then generate the loop. And then we're going to return it out. So there's no special for token or anything like that, which is a really cool thing, and that's why I like this lecture so much. And let's see. Yep. We're going to do scripts, run, examples, test 6. And I'll show you test 6 in a second. So this should do the exact same thing as our last while loop did. It should print out the numbers 1 through 10. Clang test6.ll. And let's call test 6. Boom, 1 through 10. It's a very fun thing to look at the diff between the while branch and the for branch, because it's literally like 15-ish lines of code, which is a really cool thing. One commit, 97 through 125. Okay, so like 30 lines of code plus 3, and then add our test. So super simple, and now we've got, that program looks a whole lot more like C than anything we've been doing before, right? And then I've added those to our PyTest suite, and that's all the code we're writing today. So I'm going to introduce the optional homework now. I suggest that you add in break and continue statements. You have all the tools to do it. It is going to be very easy. It's a fun exercise, and you're going to be surprised at how little code you actually have to write for it. And then quick note, I recommend that everyone should keep up to date on the assignments. I know if you're like a week or two behind, that's not a big deal. But if you haven't written any code yet, or you haven't even forked the repository or anything, I am worried that you're probably not going to complete the course. So you have to have momentum to get to that ending point, and already through, we didn't use the first week of school. We've got spring break. You've probably got 2 weeks minimum of midterms and finals, maybe 3 weeks if you have 2 sets of midterms. So if you haven't started yet and you want to actually finish the class, strongly recommend you get parsing done by the end of the week. Otherwise, I think you are probably not going to be successful in completing the course. So that is all I have for today. Are there any questions? Nope.